So we're still in chapter 5, talking about polar coordinates and vectors. And section 5.3 is an interesting kind of side note about the complex plane and de Moivre's theorem. So it's going to be related to polar coordinates, but it's going to be really important that you have a clear distinction in your mind between when we're working with polar coordinates of rectangular points and when we're working in the complex plane. So let's look at the objectives, and the first one is going to be just to plot points in the complex plane. So you'll learn what the complex plane is. And then we're going to convert a complex number this is going to sound familiar, from rectangular form to polar form. And then we're going to find products and quotients of complex numbers in polar form. Then the fourth objective is to use de Moivre's theorem. And the last is going to be to find complex roots. Okay, so first we're going to plot points in the complex plane. And you might want to review complex numbers. And here's instructions that tell you where. You look in Appendix 6 on page A42 in the textbook, and there's a little review of complex numbers. So just a reminder that the standard form of a complex number is a plus bi. So for instance, 1/2 plus 7/2 I. This is in correct standard form. If you write 1/2 plus 7i over 2, that's not correct. The b needs to be sitting right here next to the I. So make sure you use the proper standard form. So the number I is the square root of -1, and you should have seen this before. If you haven't, then you're going to have to learn it really quickly. A is called the real part, and B is called the imaginary part. So A and B are both real numbers, but when you put them together and say A plus BI, then that is a complex number. So in the complex plane, the complex number a plus bi is plotted as the point a comma b. So if you have the number 2 plus I, you label your axes real and imaginary, and you say this has a real number part of 2 and then an imaginary part of 1. So the point 2, 1 represents this complex number in the complex plane. So here's another example. If I have -3 minus 2i, I label my axes real and imaginary, and I go -3 on the real axis and then down 2 on the imaginary direction, and the point -3, -2 represents the complex number -3 minus 2i in the complex plane. So the letter Z is commonly used to represent an arbitrary complex number, just any old generic complex number. So suppose Z equals X plus YI is some complex number. Then we define something called the magnitude or the modulus of Z, and we use absolute value notation. And it's the distance from the origin to the point. So you can see how if you have the point 3, 4, so 3, 4, which in the imaginary and real axes of the complex plane represents the number 3 plus 4i, then you can see that the distance from the origin to this point that's representing that complex number is going to be 5, which is 3 squared plus 4 squared, square root of that. So that's the modulus or the magnitude of z, the complex number. Okay, so then you've also learned about something called the complex conjugate. So the complex conjugate of the complex number a plus bi is a minus bi. Well, these numbers are conjugates of each other. So a plus bi and a minus bi are conjugates of each other. And you actually know something else that works this way too? Reciprocals. If you say x and 1 over x, those are reciprocals of each other. You don't just say that one is the reciprocal of the other. It's a back and forth relationship where they're reciprocals of each other. So these are conjugates of each other. So if we have the complex number z that's a plus bi, so we have z is a plus bi, then we put a bar over the top, that's the conjugate, that's the symbolic notation for the conjugate, a minus bi. Then let's see what happens if we multiply z, which is a plus bi, by z bar, which is a minus bi. And if you forget how to do this, make sure to go to that appendix and refresh your memory, because we're going to get a squared minus abi plus abi minus b squared I squared. Well, abi and negative abi cancel each other out. I squared is the same thing as -1, so you get a squared plus b squared, which is a real number. So what we have just showed is whenever you multiply a complex number by its conjugate, you get a real number. Because we did it in general, then it means it's always true. Okay, so now objective 2 is to convert a complex number from rectangular form, because you can see that we've been working in a rectangular complex plane, to polar form, because it's going to be much more convenient to work with the numbers in their polar form. So z equals a plus bi is a complex number written in rectangular, or it's also called Cartesian form. So that's when we draw these axes and we say this is the real axis and this is the imaginary axis, and we use the same sort of rectangular coordinate system that we're used to. So to write the coordinates of that same point in polar coordinates, we use what we've learned previously and we say, oh, we need to convert using a equals r cosine theta and b equals r sine theta, and we're always going to have r be positive, or at the smallest 0, but never negative, and we're always going to have theta between 0 and 2 pi. So the number a plus bi is going to be r cosine theta plus r sine theta I. So we've written a complex number that was given in rectangular form in polar form. So this is called polar form of a complex number. So notice the difference between what you've learned previously. There were no i's. As soon as there's an I, it's a complex number. So then you factor out the r to actually get the formal polar form. So the r sits out at the front, and you have cosine theta plus I sine theta, and this is the polar form of a complex number. So theta is called the argument of the complex number, and we already talked about the modulus, or the magnitude of the complex number, is the r. So if you have the complex number 1, or let's do 2. 2 in the real direction and 2 in the imaginary direction. So that would be 2, 2 in the complex plane, which represents the complex number 2 plus 2i. And then we wanted to write it in polar form. We already know how to do that. So let's use that as our example. We'll have 2, 2, which is a point in the complex plane, but recall that it represents the complex number 2 plus 2i. So we can figure out the magnitude or the distance from the center, which is going to be the r. So it's going to be 2 squared plus 2 squared, the square root of that. So that's going to be 2 root 2. So r equals 2 root 2. Then to find this theta, it's the same theta that we already learned about in polar coordinates. So you can see that the tangent of theta is going to be 2 over 2 or 1. So theta must be 45 degrees or pi over 4. So if no specific instructions are given, use radians. But notice in this instruction set here for the exercises to follow, it says express the argument in degrees. So in complex form, the rectangular form, we have 2 plus 2i. So we say that's equal to 2 root 2 times the cosine of 45 degrees plus I sine of 45 degrees. And this is called the polar form of the complex number. Okay, so here's some exercises. I'm going to do the first one here, and then we'll do the rest in class. We have -1 plus I. So here's the point in the complex plane. So it's got coordinates -1, 1, but that represents this complex number, -1 plus I. So we can see that the r is going to be -1 squared plus 1 squared, and then the square root of that. So it's going to be square root of 2. And then we need to find the theta. Well, the process is going to be the same as it was for finding the polar coordinates of the point. So this is going to be theta reference. The tangent of theta reference is going to be the absolute value of the y over the x. So that's going to be 1. So theta reference is 45 degrees, but we can see we're in quadrant 2. So theta is going to be 135 degrees. So to write the complex number -1 plus I in polar form, it's going to be square root of 2 times the cosine of 135 degrees plus I sine 135 degrees. So that's going to be your answer. Here is this complex number plotted and then written in polar form. So we'll do the other one in class together. And then going the other way is much easier, but you are going to have to think about your special angles. So going the other way is write the complex number in rectangular form. So we'll do those in class together because that way is a lot easier. So I don't think you need to see a complex movie about that one. So I'm going to go ahead and stop the movie here so I don't run out of time for the next two objectives. And then I'll make a continuation.